In this video, I'm going to talk about my research topic, which is estimation for generalized additive models using Bayesian model selection with mixtures of G-priors. Okay, so first of all, I'm going to introduce what is a generalized additive model is and our strategy, which is to use basis expansion and Bayesian model selection. In the second section, we're going to introduce our prior specification, and also we're going to touch on the mixtures of G-priors and we're going to explain the differences among those in terms of penalty functions. And we're going to end this presentation with numerical study and applications. Right. So we believe our main contributions are threefold. First of all, we have reviewed and extended estimation methods for generalized additive models using Bayesian model selections using G-priors. So the idea of using BMS to estimate the generalized additive models is not itself new, but it was limited to Gaussian response or limited to univariate function. We have extended those to be additive for also for the exponential family distribution. And secondly, we have proposed a simple slice sampler algorithm to sample from a class of generalized beta distributions. So generalized beta distributions are frequently used in Bayesian model selection rhythm, but the sampling from it were not very straightforward. But we found out that if we use a simple slice sampler, then we can sample from it by something similar to Gibbs sampler without having to manually configure the envelope for rejection sampling. And finally, we have discussed a new perspective on the behavior of mixed G-priors with a focus on the base factors as penalty functions with respect to the model complexity and goodness of fit. I'm going to explain about this more in the detail later. But first, let's talk about some of the basic concepts here. So generalized additive models is the extension of generalized linear models, where each covariates are allowed to be nonlinear, right? But there's no interaction. So for example, if we have two covariates, then we are using these marginal nonlinear functions to construct this two-dimensional surface here. So since there's no interactions, the number of parameters are confined, more or less confined compared to other non-parametric methods. And this is why it's sometimes called semi-parametric method. Okay, and in order to estimate this nonlinear function, we're going to use basis expansions and to draw a spline. So spline is a piecewise polynomials, right? That is constructed via a linear combination of basis function, which is itself a piecewise polynomials. And the piecewise polynomials are the polynomials that are the smooth function that are polynomials inside the interval that is determined by knots. So these circles correspond to knots, and within this interval, this estimate here, this function here is a piecewise, is polynomial, right? And we're going to use a third-degree polynomials, but also we're going to add natural cubic spline, natural boundary condition, so that the resulting spline is linear outside the boundary knots. We're doing that because in order to control for the erratic or irregular behavior around the boundary, which is commonly observed if you use a polynomial basis, right? And also we have introduced a slight modification of the usual formulation of the natural cubic spline and its benefits are twofold. First of all, if there is zero number of knots, then our function estimate reduces to linear function. So our formulation of generalized additive models naturally encompass a partially linear models. And secondly, with this formulation, the addition and deletion of knot directly corresponds to addition or elimination of a column in the design matrix, right? Without having to alter the rest of the columns, right? Okay, and that makes applying the variable selection algorithm to our estimation methods very straightforward, right? Sorry. So, okay, so how do we choose the number and locations of knots? So each number and each combination of number and location of knots can be thought of as a model. So and we're gonna use a Bayesian model selection to determine the dot configuration, right? What does it mean is that what it means is that we're going to use a Bayes rule to sample from the space of models, right? So we're going to use, so we want to like sample from the knots that are deemed more appropriate with respect to the data, right? And in order to do that, we need a marginal posterior. We need marginal posterior of each model, and we're using the Bayes rule to use. Of course, we have to use the Bayes rule, and the Bayes rule has two components. First component is the prior of knots, and the second component is the model evidence. So prior of knots is the prior on the number of locations of knots, and we're gonna touch on that later. But the biggest obstacle here is to deriving the model evidence. So the model evidence is a marginal likelihood of the model where across all the possible splines that can be drawn under the model. So what it means is that inside this model where there are only two number of knots, so each dotted curve here corresponds to a specific value of the regression and spline coefficient beta. And across all these possibilities, we have to calculate the marginal likelihood of this psi 1, which in turn works as a weight of this model to calculate the model average estimates, which is our final estimates of this function, right? And that involves computing this integral, and which involves the high dimensional integration. And then this integration tractable, analytically tractable if only the response is normal, because in most cases we're gonna use a normal prior for the beta, right? But for non-normal distribution, this you have to approximate it. And in 2018, in a paper by Lee and Clyde in JASA paper, they have introduced a specific prior for the regression coefficients, which allows for a tractable Laplace approximation of this model evidence, and we're going to use that. And so in the rest of the paper, in the rest of the presentation, we're going to first introduce the mixtures of G priors to calculate the model evidence, and also we're going to touch on the prior for the knot configurations. So mixtures of G priors. In Lee and Clyde 2018 paper, they have introduced a locally orthogonal G prior, and the name. So this is the extension of the generalized G prior to generalized linear model to allow for a tractable approximation of the model evidence here. All right, and that this model evidence, it depends on number of G, the value of G. And this value of G determines the function estimate. So if you use G that is too small, the function estimate would be too wobbly, too unstable, because too many knots are included. And if you use G that are too large, then we are favoring simpler models because knots are penalized. The adding knots are penalized too much. So we want this G to be to sit in between, to be appropriate with respect to the data. So we want G to be data dependent. So there are two methods for that. First of all is to use a fixed number of G. In the most common way is to set G to equal to n, which is suggested by Kost and Wasserman, and it is called unit information prior. And this has been the most popular method in the literature when Bayesian model selection is used for non-parametric regression. Or we can use the the optimal value of G by using empirical Bayes. But in this paper, we are focusing on the mixtures of G priors. So mixtures of G priors is if we specify a prior on G, then this prior here becomes mixed over the possible value of G. So this is why it's called mixtures of G priors. And the specific form, there has been many variants of mixture G priors proposed in the literature, but in the Lee and Clyde paper, they showed that all the priors, Hiroto proposed, in fact a class of specific cases of truncate compound confluent hypergeometric distribution. Right? This is a generalized. This is also a variant of generalized beta distribution where the supports or the skewness or the shape can be freely determined by a total of 6 parameters, right? So if you use these priors, then if you plot these priors in terms of G, then we have these densities, these log densities, and there are two kinds of the G priors, priors on G that are different in terms of the shape. In the first case, which is called G01, G to the big O1, their prior density does not change with the number of the sample, right? As you can see, when the n is 200, 500, 1000, this uniform hyper G prior does not change. For the other priors, hyper G over n or intrinsic robust, general no adapted beta prime, if the size of the sample increases, then more and more of a prior mass is concentrated to a larger value of G. So this is why these priors are called a mixtures of G priors of G to the big O n. And in this, under this classification, the unit information also belongs to G to the big O n, because as you can see, this corresponds to a point mass prior, Dirac delta mass prior on the point, which is n, right? And also shifts with the n, right? Obviously, okay. And the question is which prior to use for our purpose to estimate generalized models. Some priors would tend to produce too complex function estimates, and some priors would lead to too simple function estimates. We want to figure out which choice of G is ideal in our purpose, and we're going to touch on that later in the third section. So anyway, so for now, if we use the prior on G, if we specify a prior on G, then we have to face a different model evidence here. Because we have to integrate out the G here, and it becomes the formula. And also we have the posterior distribution of the G, which is also a truncated compound confluent hypergeometric distribution. So the evaluation of this transcendental formula here, the expression here is very straightforward by using one-dimensional Gaussian chronological quadrature numerical integration. And also sampling from this distribution is also straightforward by using the general slice sampler. This is not, I'm not referring to the slice sampler of the variant of the Neil in the 2004 paper, but more of a general version. So, in fact, in the 2018 Lee and Clyde paper, they have not discussed how to sample from the posterior, and in their code, they had just plugged in the posterior mean to sample the models, to sample for the model specific coefficient, right? And but that could be admissible for linear models, but in our case, since we're doing a semi-parametric regression, we want we want all the uncertainties in G to be accounted. So that's why we are sampling from the G here to enable the fully Bayesian information. Okay. So let's talk about a little about the priors for knots. So the priors for knots consists of two components. The first is the number of the knots, and the second is the location of the knots given the numbers. So we're gonna use a uniform prior for the number of knots. But there are three strategies to determine the locations of knots. In even knot strategy, the locations are predetermined to be evenly spaced. In variable selection knot, the locations are it should be sampled from a candidate grid point of knots. And in free knot, there's no restrictions. And obviously, the free knot is the most flexible, but it also takes the most amount of time, the longest time to sample from the posterior, for the posterior computation. So there is a trade-off between model flexibility and predictive performance, and the posterior computational experience, right? And throughout this, with the simulation methods, we have found the variable selection knot are ideal in terms of predictive performance and also in terms of computation space, because obviously it sits in between. Okay, but So let's talk about the mixtures of g priors and penalty functions. So so our main one of our main research question was how the different choice of g priors lead to different behavioral model selection. Because obviously we were seeing different results in the simulation study, and we have tried our best to explain the results, right? And this is the best so far I have ever to come up with. And so let's assume a hypothetical two-knot configuration. So these two-knot configuration, two knots have a equal have exactly equal fit. So the maximum likelihood estimate under each model are identical, right? So the shape of the function is exactly similar, right? Exactly identical, right? But however, the knot in the denominator, the numerator here, use one more knot than the second knot here. Then the base factor, which is a ratio of model evidence, is going to penalize the model in the numerator, right? Because it's going to have a lower model evidence, right? Because apparently they're using like one more knot without any improvement in the fit, right? And that in that respect, the base factor can be interpreted as a penalty functions under this specific scenario. And that formula and that quantity, the base factor, if we use, is given by this for a fixed number of g, right, which is smaller than 1 apparently, obviously. But if you use a mixture of g priors, then the quantity becomes a posterior mean of this quantity under the model in the denominator, right? And this posterior quantity is a function of the fit and size of the model here, psi j, right? This means that the penalty of the mixture of g priors are adaptive. They depend on the number and the size and the fit of the model in comparison, right? So our main observation are as follows, and this also holds for Gaussian and on exponential family distribution. First of all, the penalty function of mixtures of g priors depends both on the model size, right, and the goodness of the fit. The penalty gets weaker as the model size increases or the fit deteriorates, right? This means is that if your model is using many knots, many variables, but have a poor fit, then if you use the mixtures of g priors tend to add more knots, right? Because they want to explain the data better. We are using more knots, right? And secondly, compared to the fixed choice of g, the mixtures of g priors tend to add more knots, especially if the current model has poor fit and many knots. This is what I have said before, right? And within the mixtures of g priors, GO1 priors, the priors whose shape does not change with n, allow comparatively more knots than GON, and especially so in the region of poor fit. And let's see how we have come up with these observations. So this is the plot of the base factor. I said the base factor depends on model evidence. Depends on the complexity, right? The size, the number of variables in the model, and also the fit of the model. If you see, the thicker colored indicates the higher penalty. The unit information has the highest degree of penalty, and does not depends on the size or the fit. But these two here, the GO1 priors, in the region of poor fit, there's literally no change in the penalty. The penalty is so low here. So if your model is playing around here, then chances are you're going to gravitate towards the region of many more knots. Alright? And also there's also the case for the other GON priors, but that degree is much weaker, right, than the GO1 priors, which means the penalty still exists. The penalty is still, there's also a penalty for this adding more knots here. And this next plot is a cross section of this plots. So in this region of poor, the fit is 0.02, which is a poor fit, right? And obviously the penalty function, penalty increase scales with the size of the sample, right? And the unit information prior imposed the heaviest penalty, but the mixed source of G priors, their penalty, the complex penalty is lower here. When there is more added, there are more variables here. Yeah, right. And the degree of penalty gets weaker in the order of beta prior generalized null, and also gets weaker in the hyper G, the intrinsic and robust priors, and gets the weakest and because more the lowest for the GO1 priors, right? So so I'm not trying to generalize this. I'm not trying to say this result also holds for all other cases, because if keep in mind we're playing with the toy example here when the two models have exactly the same fit, and that is unlikely to be true in real world. But what I'm trying to do here is that we're trying to explain the results as best as we can, because in the next section in the simulation study we are indeed observing these differences, right? So this leads us to numerical study. So we're using three functions here, and we are running a univariate model, right? To better discern the effect of mixtures of these priors, and we are using the Bernoulli models, right? Bernoulli logistic regression. So this function is a moderately nonlinear function, right? And if you use unit information prior, then the estimates tend to be the very, very flat. It means that this unit information prior failed to capture the variation here by penalizing knots here. But for GO1 priors here, they're very complex. They're adding unnecessarily many more knots. But the lower prior here, the GON priors, sits in the middle, and especially the robust and intrinsic prior appears to be better. And that result also comes through with this RMSE and coverage property, right? So the RMSE is slightly higher for the GO1 priors, but their coverage is better than the others. So one can say these parts would be better. GO1 parts is better. But if you run the simulation for complex results, then the GO1 priors tend to be too complex in this stable region, right? They just add more knots here, right? And this leads to higher MSE for this function, even if they have higher coverage property, right? And obviously the unit information is very flat, and the other priors, some of them are flat, but apparently they are capturing the variations here, and especially the robust and intrinsic, they are doing a better job in this spatially inhomogeneous region here. And that is shown as the coverage property here. Their coverage is better than the other GON priors, right? And these differences, because especially marked when you're comparing the estimation for the linear function. GO1 very complex here. This is not good, right? And robust and intrinsic is very stable here. So their RMSE, the GO1 RMSE is high, but the other is very stable. So what is the result here? So our conclusion is that difference between priors and G become noticeable at small sample size. Apparently, it's obviously, and the unit information prior generally underperforms for a nonlinear function estimate, preferring simplistic models. And among the mixture of such priors, robust and intrinsic prior ideal almost always. The beta prime and generalized null tends to over smooth, whereas the uniform hyper G over N tends to under smooth, right? Under smooth means they are not doing the penalizing thing enough, right? So our result is that we set robust to be our default choice, because the posterior sampling for the robust is very much simpler, because the posterior follows the TCCS distribution, but for robust distribution it reduces to truncated gamma for exponential value response, or just the Gaussian hypergeometric for a Gaussian regression model. And sampling from that only requires sampling from Gaussian hypergeometric only requires additional 1 or 2 auxiliary variables, so the mixing is much better. Okay, so in the second part of the numerical study, we have compared our BMS-based methods with other methods. All the other methods, pre-existing other methods, are based on Bayesian P-spline. So what they are doing is that instead of playing around with the knots itself, they're fixing the knots to be a grid point, and they are using smoothing parameter to how do you say determine that the regularize the function estimate to like smooth the function estimates, right? And though there are three packages out there that are different in terms of how to determine the smoothing parameter. So the MGCB use the optimized value of lambda, the smoothing parameter, by either using empirical base or using the cross validation, or the R2 basic sample the lambda, which is fully Bayesian method, or the BLPSR, which is relatively recent. You integrate out the lambda and sample from the marginal of the posterior, beta posterior, right? And we are using the exact same functions, but in this case we are using the multivariate. So we are using the additive of the model of three function components, right? And also we are showing the result for Bernoulli distribution. We have done the same thing for Gaussian and Poisson alike, and we have reached to a similar conclusions, right? So the result is that for this BLPSR basics, they tend to be overly smooth. They don't seem to capture the curve here, right? And also holds for here. So and also for this function, they fail to capture the variations here. But MGCB tends to do better, right? It appears to better here and also here. But in terms of estimating linear function, MGCB tends to produce a unnecessarily complex function. It means that when it comes to estimating simple functions, MGCB tend to oversmooth, right? Tend to undersmooth, right? I mean, so our result is that R2 base X and BLPS are often oversmooth with excessive penalizers, and then those are not fit for locally varying functions because they're only using one single smoothing parameter, right? And if you use one single smoothing parameter, then you are penalizing, you are regularizing, altering the shape globally on the entire domain. So you cannot make the function to be varying in one part and stable in another part. So this is the inherent limitation of these methods. Compared to that, MGCB allows for adaptive estimation using locally varying smoothing parameter. It's similar to global local shrinkage prior in Bayesian model selection. But anyway, but MGCB adaptive they tend to work better for spatially invariant functions. But these lead to a higher MSE and lower coverage for others. As you can see here, the MSE for MGCB adaptives were higher here for the simple functions here, right? Because they're producing overly, complex estimates here. And another drawback for MGCB is that we do not know in practice whether the function is locally varying or not locally varying. And the downside is that we cannot. There's no way for us to know that in advance. But MGCB so users have to set their option in advance. So there's unrealistic in many cases. Compared to that, in contrast, the Bayesian model selection methods, free knot and variable selection knot naturally allows for locally estimation local varying because they're determining the sample of the posterior distribution of knots, right? And among those, between those and variable selection knots, we saw that it is better in terms of sampling efficiency. So we measure the sampling efficiency as a ratio of effective sample to sample size to runtime. So it means a number of effective sample that can be sampled at 1 second the CPU runtime. As you can see, variable selection knot can sample many more samples in the same amount of time, right? It means that mixing for variable selection knot is better than the free knot. And even knot although these are not unfit for local varying functions, these are very fast, and these performance are comparable to other functions. For example, for these functions, not varying functions, their results are really comparable to other options here. So I found that in practice, I have used even knot strategy. I found this strategy very useful for pilot analysis, for the exploited data analysis, because if you use variable selection node, we have to wait several minutes, right, to get the estimate. And if you're doing exploited data analysis, then even that can be very useful, right? Okay, so the last part is the applications. Okay, so I'm going to be very brief here. So we use the Boston housing price for Gaussian additive, and the results here, and we have used these 12, additive function components, and those are estimates very nicely. Some of them appear to be very linear. So apparently, we want to answer what is the probability of the function to be linear, and if we use Bayesian model selection, and our formulation of the basic function provides an answer to this question. We have an answer that we can say we calculate the marginal probability of this function to be linear, where there's no node is selected, and that is the probability is 78% for this Indus, and 88% for GN, right? And data analysts can, even practitioner can make their judgments whether to make this variable to be linear or non-linear, or just adding it to be making it to be linear. But that decision has to be followed by a model diagnostics, right? But anyway, this Bayesian model selection, our method is really helpful because it provides these kind of answers, right? This is very intuitive answers. What is the probability of this function to be linear, right? And also run the same thing for the logistic regression model with 7 additive components, and this is the result here. And also we have the posterior probability of this glucose to be linear, and pressure and tripses to be linear is 80%, right? Okay, and that concludes our presentation, and thank you for listening to this long presentation. I tried to keep it short, but it has become 32 minutes. Okay, thank you.